Hello physics class, this is Dr. Brenzi here. These are some notes on Unit 1 talking about velocity, speed, and acceleration. And I wanted to give these notes to you because I did go through them very quickly in class. And I thought it would be good for, especially as you're going through the review problems tonight, to have a guide to help you out. And I did tell you that I was going to show you those graphs as well at the very end. And I just decided why not just turn this into a video and go through the whole thing. So that's what I'm going to do. In my notes, if you just want to skip ahead to the actual graphs themselves, I'll give you a timestamp that you can forward ahead into and find those graphs so that you don't have to watch the rest of the video if you don't want to. Alright, so talking about velocity versus speed. So there is a difference between velocity and speed. So let's say that I have a student who moves 20 meters toward the right in 4 seconds and then immediately turns around and goes negative 15 meters, that is 15 meters to the left, in 2 seconds after that. So let's talk about displacement. So displacement is 20 minus 15, which is 5 meters. So in 6 seconds, this person has a displacement of positive 5 meters. In other words, they have ended 5 meters to the right of where they began their trip. So if I want to calculate the average velocity, I'd have to take the change in displacement divided by the change in time, and I end up with 0.83 meters per second. Now their distance that they covered, however, is not 20 minus 15, but is 20 plus 15. They covered a total distance of 35 meters in that same 6 seconds. So their average speed is going to be that 35 divided by 6, which is 5.8 meters per second. Now, these numbers look very different, don't they? They look very different because we have changed our velocity during our travel here. So our average speed does not match our average velocity. Now, here's just a little something to kind of wrap your mind around, is that if I just had another student who just walked that plus 5 meters over 6 seconds and made it directly from the start to the beginning of that time, what would their average velocity be? Well, it would end up being the same thing as the average velocity for the first trip. But their average speed would be also 5 divided by 6, so their average speed would be a lot less. You can imagine that this person in the green is walking at a much slower speed than the person who is going from the right and then turning around and coming back in that 6 seconds. Okay, so that is a way to think of velocity and speed. So velocity goes along with change in displacement over time. Speed is the change in distance over time. Now let's talk about acceleration. The acceleration is a kind of a tougher topic to wrap our minds around. So what I'm going to do is I'm going to draw a graph of velocity versus time. And I'm going to use a speedometer at the top right hand corner to help us. So let's say that after 10 seconds, or actually I begin at 0 seconds with my needle at 0 meters per second. And let's say that after 10 seconds, I look down after I've hit the gas pedal for that 10 seconds, and I notice that my speed, or my velocity, excuse me, went up to 20 meters per second. Okay. I'm going to assume that my velocity and my speed are the same thing. In other words, that I'm always going in the same direction. That way we can look at this speedometer and think of velocity, because that's probably the best way for us to think about how velocity acceleration works. So after 10 seconds, my speedometer needle is at the 20 meters per second mark. So I can graph that as this point right here. Now, after 20 seconds total time, I look down and I find out my speedometer needle has gone up to 30 meters per second. Ooh, that doesn't look right because I put, actually, this is 40, not 30, sorry. So after 20 seconds, I have a speed of 40 meters per second. And then after 30 seconds, I'm up to 60, and after 40 seconds, I'm up to 80. And when I plot this, it makes a nice straight line. And the average acceleration that I experience is the change in velocity divided by the change in time. Change in velocity is 80 meters per second, and the change in velocity, or time, excuse me, is 40 seconds. So I can say that my average acceleration is 2 meters per second every second, or I can say 2 meters per second squared. So acceleration is the rate at which this needle goes up, increases, or goes down, decreases. So a very fast acceleration, high acceleration, would see this needle going up very rapidly. And a slow acceleration would see this needle going up only very, very slowly over time. Okay. Now, this graph was confusing. I'm going to erase this thing, and I'm going to show you a different graph that I hope will make a lot more sense. So let's say that our student Johnny is late for class, so he zips out of the bathroom door and covers 20 meters in 5 seconds and is in a big hurry to get to class. And then the teacher comes out into the hallway and says, "Johnny, stop running so fast." So Johnny actually slows down, and over the next 10 seconds, from 5 to 15 seconds, he only covers another distance of 5 meters. So he's actually walking very slowly. So this is what a graph of, this is actually a graph of distance or displacement versus time. Okay. Since Johnny's going in the same direction always, we can either say that this is distance or displacement, but I should call it displacement. Okay, so instantaneous velocity is the velocity at a given instant. So if I want to know what Johnny's velocity is at 2 seconds, I would look up this point at 2 seconds and see that the slope of the line at this point is 4 meters per second. I could do the same thing at another time at 4 seconds. I could look up 4 seconds, go up, see this point, and ask myself, what is the slope of the line at this point? And it is still 4 meters per second. So my instantaneous velocity at this point is 4 meters per second, and my instantaneous velocity is 4 meters per second at this point. Now later on, after the teacher came out in the hallway and yelled at Johnny for going too fast, at 6 seconds, I'd go over here to 6 seconds, go up on my graph, and ask myself, what is the slope of the line right here? And I would notice that it is 0.5 meters per second. And also at 8 seconds, I could do the same thing again, go up here and discover that the slope of the line at this point is 0.5 meters per second. So instantaneous velocity is all about asking, okay, what is the slope of the line at this moment, at this very time? Average velocity, however, is asking what is the average velocity that is happening over a time range. So I can ask myself, what is the average velocity between 0 and 5 seconds? So what I would do is I would find the velocity at the beginning point, which is 0, find the velocity at the end point, which is 20, and then use my velocity formula, change in displacement over change in time, and come up with 4 meters per second. Now, because Johnny was going at a constant rate of displacement over time, then the average velocity and then the instantaneous velocity happen to be the same. But after 5 seconds, Johnny changes his instantaneous velocity so that during these times his velocity is 0.5 meters per second. So if I wanted to calculate the average velocity between 5 and 15 seconds, I would need a beginning point, I would need an end point, and I would then connect those two and find the slope of the line. And so the average velocity between 5 and 15 seconds is 0.5 meters per second. Now things get interesting when I ask myself, okay, what is the average velocity over 0 to 15 seconds? So I need the beginning point, I need the end point at 15 seconds, and then I need to connect those two with a straight line. And the slope of this straight line will give me my average velocity. So we covered 25 meters of displacement over 15 total seconds. Divide those two and you get 1.7 meters per second. So Johnny was running faster than his average velocity from 0 to 5 seconds, but then he was going slower than his average velocity from 5 to 15 seconds. And you'll notice, and this is very important, that this average velocity is not the average of these two numbers. If you take the average of these two numbers, you're going to get something that's different than 1.7. So be very careful about that. You need to take total displacement, change in displacement over change in time to find average velocity. Okay, now on to graphs. So this is the point that you've been waiting for if you were waiting for graphs. So if I have a displacement versus time graph, I can find the velocity by calculating the slope of this graph. So let's go ahead and do that. So I'm going to pick a point, and it looks like after 1 second, what's the slope of this line at 1 second? Well, I can see that its slope is going to be 2 over 1, which is 2 meters per second. Now, if I pick another point on the line and ask myself what is the slope of the line near that point, I'm still going to get a number of 2 over 1. And no matter what point I pick along this line, I'm always going to get 2 over 1. So a line for displacement versus time will give me a constant velocity. The velocity will not change. Now I can take the slope of a velocity versus time graph to figure out what acceleration is. So let's do that. Let's ask ourselves, okay, if I'm looking at time 1 second, what is the slope of the line near that point? And it happens to be 0 because we're not changing velocity up or down. If I look at any other point on this line, what's the velocity or the slope of the line near this point? Well, it's also 0. And then I can go on down the line, and I'm going to find that every point along this graph will give me a slope of 0. Okay. So constant velocity means that our acceleration is 0. Now, if I happen to have a velocity that is not constant, well, I can still take the slope of this line to find out what my acceleration is. And the slope of this line is 1 meter per second here, it's 1 meter per second there, it's 1 meter per second here, it's 1 meter per second there. So I'm just going to get a series of dots and all of them have a y value of 1 meter per second, or 1 meter per second squared. So when you see a line for a velocity versus time graph, you know that your acceleration is constant. Well, what if, actually before I go on to that, there's a similar pattern when you're being given displacement in a word problem, let's say. So let's say in this word problem, Johnny is at 0.5 meters 1 second after he starts walking, and he's at a distance of 1.5 meters after 3 seconds of walking. What is his average velocity? And what we can do is we can use the slope formula, change in distance over, displacement over change in time. So delta D, 1.5 minus 0.5 over delta T, which is 3 minus 1, and we will get an average velocity of 0.5 meters per second. We can do the same thing if we're given 2 points of 2 pieces of information about this person's velocity at 2 different times. We can take the change in velocity divided by the change in time, and that will give us our average acceleration. So if we ended up here after 6 seconds at negative 0.25, take the difference of that from our initial position, so that means the person moved negative 0.75 meters per second. That's how much their speed, or excuse me, velocity changed. And then that changed over a time period of 4 seconds. So when we take negative 0.75, the change in velocity, divided by the change in time, we get an acceleration of negative 0.188 meters per second every second. So this has a very similar relationship to finding slopes on a graph. So if you want to figure out, what is the formula for average velocity? You just need to remember, oh yeah, average velocity is a slope of a displacement versus time graph. What if I need to go the other way? What if I'm being given a velocity graph and I need to figure out the displacement graph? Well, the trick to this is to actually find the area underneath the graph. So after 1 second, I would find the area enclosed by this rectangle from 0 to 1 second, and from the x-axis up to the graph itself. And if I were to do this, I have a rectangle that is 1 second by 2 meters per second. So 1 times 2 is 2, which means that after 1 second, my displacement is positive 2. And then I can do the same thing for 2 seconds. Notice that I'm taking the area under the graph from 0 to 2 seconds. And when I do that, I find out that the area of this rectangle is 4 meters. So the displacement would be 4 meters there. And then I can continue to do that, and you'll notice that when I do that, I end up with a line. I can do the same thing for acceleration. Let's say I'm given this acceleration graph. Okay, so let's assume that I start off with a velocity equal to 0 meters per second. I am going to find the area underneath this graph, and that means that after 1 second, my velocity is 1 meter per second. Do the same thing after 2 seconds, and I find that my velocity is 2 meters per second. And you can keep on going and discover that this is going to create a line. Well, let's say I have this and want to find displacement graph. Well, I can do the same thing. I'm going to find the area under the graph from 0 to 1 seconds. Well, this time I have a triangle, so I have 1/2 base times height. So 1/2 times 1 is 0.5. So after 1 second, I've changed my displacement by plus 0.5. After 2 seconds, let's find the area under there, and it comes out to be 2 times 2 times a half, which ends up being 2 meters. And I can do that for 3 seconds, find the area under the graph, and find out that it has a displacement of 4.5 seconds. Now this is not going to make a line, is it? As a matter of fact, the shape that it makes ends up being a parabola. So whenever you have constant acceleration, you will have velocity that is a line with a slope. And when you have velocity that is a line with a slope, you will have a displacement that has the shape of a parabola. Okay, a little bit of a long video, but I felt it was pretty necessary for those of us who felt really lost during class today. So hopefully this helps you out. If you have any further questions, come see me during my office hours tomorrow after school, and I'd be glad to help you out. All right, talk to you later. Bye.